In today's lesson, we're going to talk about inverse functions. Recall that a function is an assignment between x values and y values. The x values correspond to the domain and the y values correspond to the range. But there's really one important restriction with functions, that each element of the domain can only be assigned to one element of the range. This means that in order to be a function, there can only be one output for every input. As you can see in the picture above, there's two relations, f and h. While f is a function because each input corresponds to exactly one output, h is not a function because one in the domain is assigned to more than one value in the range. Let's continue this discussion, but with regards to inverse functions now. So in the pictures below, you can see the picture on the left represents the function. The picture on the right represents the inverse of that function. In regards to the first picture on the left, you can see that when I plug 1 in, I get out -1. When I plug 2 in, I get out 1. 3, I get out 5. 5, I get out 7. 7, I get out 11. But with the inverse function, the exact opposite takes place. I get -1 plugged in, I get out 1. 1 plugged in, I get out 2. 5 gives me out 3. 7 gives me out 5. 11 gives me out 7. So based on this relationship, there's really two important things to note here. Number one, it's important to notice that the domain and range of f of x, our function, swaps roles with the inverse relation. That means that the domain of my function now became the range of my inverse function, and the range of my function is now the domain of my inverse function. This fact will be super important moving forward. The second important thing to note is that the notation for inverse relations and negative exponents look very similar, but they are extremely different. So inverse of 7 denotes the inverse relationship, while f of 7 to the negative first power has a negative exponent that denotes the reciprocal. So in this particular problem, the inverse of 7 is 5, and f of 7 to the negative first is really 1 over f of 7, which is 1 over 11. Needless to say, it's very important for us not to confuse these two very different notations. Now, when it comes to proving inverses of functions, as you can see, a function and its inverse function can be described as the do and the undo functions. A function takes a starting value, performs some operation on this value, and creates an output answer. Meanwhile, the inverse function takes that output answer, performs some operation on it, and arrives back at our original function's starting value. This do and undo process can be stated as a composition of functions. A function composed with its inverse function yields the original starting value. Think of them as undoing one another and leaving you right where you started with. If functions f and g are inverses of each other, then f of g of x is equivalent to g of f of x, which has to equal x. So in example 1, determine whether f of x equals 3x plus 9 and g of x equals 1/3 x minus 3 are considered inverse functions of each other. So in order to show whether or not these two are inverses of each other, I need to take f of g of x, which says take g of x and plug it into my function of f of x. So f of x was 3x plus 9. I'm going to replace x with g of x, which in this case was 1/3 x minus 3. And I need to distribute. 3 times 1/3 is x. 3 times -3 is -9 plus 9 equals x. So since f of g of x gave me back x, that tells us that f of x and g of x have to be inverse functions of each other. All right, moving forward. At the bottom here, it says, how do we find the inverse function? So given a function f of x, how do we compute the formula for the inverse? While our function f of x gives an assignment from the x values to the y values, the inverse establishes an assignment in reverse, from the y values back to the x values. The following is the procedure to follow when wanting to find an inverse function. So here's 3 simple steps that you're always going to want to follow when finding an inverse. Step 1 is to remove the function's notation f of x and just simply replace it with y. So if you see f of x, change it to y. Step 2, find the inverse by swapping x and y in the equation and now solving for the new y. This is something that should be familiar with you as you guys learned how to do this back in intermediate algebra. And then step 3 is just remove y and replace it back with the inverse function notation. So in example 2 here up top, it says find the equation of the inverse of my function f of x equals 2 cube root of x plus 1 minus 3. So as I said before, step 1, change f of x and replace it with y. So y equals 2 cube root of x plus 1 minus 3. Step 2, go ahead and switch x and y. So now it's going to read x equals 2 cube root of y plus 1 minus 3. Now the next step is to go ahead and solve for a new y. So if I want to get y by itself, I need to add 3 to the other side. So I have x plus 3 equals 2 cube root of y plus 1. I need to get rid of the 2 on the outside, and it's being multiplied by the cube root, so I'm going to do the opposite of dividing. And so now I get x plus 3 over 2 equals cube root of y plus 1. And to get rid of a cube root, remember I'm going to cube both sides, so raise to both sides to the power of 3. And now I have y plus 1 equals x plus 3 over 2 cubed. And then I could subtract 1. So we get y equals x plus 3 over 2 cubed minus 1. And then for my last step, replace y back with the inverse notation. So this says my inverse function is equal to x plus 3 over 2 cubed minus 1. Now in this next section, we're going to look at how to graph inverse functions. Recall that the graph of a function f of x and its inverse function have a relationship. That relationship is that the domain of my function now becomes the range of my inverse function, and the range of my function becomes the domain of my inverse function. So that simply means that the points that lie on the graph of my function are going to be flip-flopped when it comes to the graph of my inverse function and vice versa. So what does that exactly mean? Well, take a look at the picture on the right, and you can see that the graph of my inverse function is a reflection of the graph of my function across the line y equals x. So take a look at that, and you can see that my function is literally reflected over that line y equals x, which makes sense because we're literally flip-flopping x and y in our relationship between functions and their inverses. So let's go ahead and take a look at our bottom example, example 3. It says find the inverse function for f of x equals x squared minus 4, then graph both the function and its inverse on the same set of axes. So starting with my function, f of x equals x squared minus 4, I know that my vertex is going to be at negative b over 2a. Well, b is 0, so 0 over anything is 0. And I have a shift down of 4, so 0, negative 4. 1, 2, 3, 4. I'll make a quick table. Put 0, negative 4 in the middle. 2 points to the left would be negative 1 and negative 2. To the right would be 1 and 2. So if I plug negative 2 in, I get negative 2 squared, which is 4, minus 4 is 0. Negative 1 squared is 1, minus 4 is negative 3. And since a parabola is symmetric, I know this has to be negative 3 as well as 0. So we got negative 2, 0, negative 1, negative 3, 1, negative 3, 2, 0. So here is my function for my quadratic, which is a parabola. Now to find the inverse function, we're going to go ahead and write this as y equals x squared minus 4. And I'm going to switch x and y. And now I need to solve for y, so I have x plus 4 equals y squared. Take the square root, and we get y equals plus or minus the square root of x plus 4. Right, now to graph this with the plus or minus sign, let's go ahead and plug in values for x. Now remember, with the radical, we need to plug in values that make the inside either 0 or bigger, because anything less than 0 would make this imaginary. So to plug in and make the inside 0, I could start at negative 4. Since negative 4 plus 4 is 0, square root of 0 is still 0. And then I can pick values to the right. Negative 3 plus 4 is 1, square root of 1 is 1. Negative 2. Negative 2 plus 4 is 2, square root of 2. Negative 1. Negative 1 plus 4 is 3. Square root of 3 is square root of 3. And I could keep doing that. And what I would get here is negative 4, 0. Just plotting my points. Negative 3, 1. 2, root 2. Negative 1, root 3. And it keeps growing in one direction. Now, that was for when it was positive square root of x plus 4. With a negative in front, we're literally just going to be reflecting this across the x-axis, as you can see here. So it looks like a sideways parabola. Now, if you take a look at the graphs of both f of x and its inverse, you can see that f of x is a function because it passes the vertical line test. However, the inverse function that we drew in, that sideways parabola, that is not a function because it does not pass the horizontal line test. So let's go ahead and write this. My inverse function from the last problem is not a function because it did not pass the vertical line test. Now, if you forgot what the vertical line test says, to test to see whether or not a graph is a function, you could draw a vertical line anywhere on that graph, and it can only hit one time. If it hits more than once, it's not considered a function. So what you could see with that sideways parabola, when I draw a vertical line, it hits the parabola more than once. So therefore, it is not a function. So it says here now, can you think of a test that you can use to determine whether a function's inverse will be a function without actually graphing the inverse? So if I know the relationship between functions and their inverses, in essence, remember that the domain and ranges flip-flop, the x and y values flip-flop, I know that since a vertical line test is used to test whether or not f of x is a function, I can now also use a horizontal line test to see if the inverse of that function is also a function. So it says here that the horizontal line test says if any horizontal line intersects the original function f of x in only one location, your function will be one-to-one and its inverse will also be a function. Now, what does it mean to be a one-to-one function? A function is a one-to-one function if and only if each second element corresponds to one and only one first element. So basically what that's saying is for each x and y value that's used, it's only used once. So you can see an example here of using the horizontal line test. So I have a function y equals f of x, and I draw in a horizontal line. Remember, you can test this at any point in the graph, so I'm just showing you more than one horizontal line test. But notice in that first graph, anywhere I draw a horizontal line, it only intersects the graph exactly one time. So that tells us that not only is the function one-to-one, but its inverse will also be a function. In example number 2 on the right, we have y equals g of x. And if I draw a horizontal line in, there is a spot where if I draw it in, it does intersect this graph more than once. So that tells me not only is the function not one-to-one, but its inverse will also not be a function. And this is going to be incredibly important when you take higher level math classes such as pre-calculus and calculus.